It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbet's Physics. What is crappinin'? Today, we're going to meet my cats. Here is Leo. See you, Leo. Maybe he'll come back in a second. We'll try one more time. Here's Leia. Say hi to the camera, Leia. Say hi. Okay, let's try Leo again. Give me a treat after Leo. Say hi, Leo. Say hi to the camera.
Leo.
Good boy. Okay. And once Leo jumps off...
Now he's back on.
The last cat I want to introduce you to is Schrodinger's cat. And here is Schrodinger's cat. What we're really going to do is learn how cats relate to quantum physics. The first thing I have to do is admit that I've been lying to you about how the model of the atom works. We've been looking at a simplified version where we have specific locations for the electron. And we talked about the probability cloud, where the electron can be at any location around the nucleus, and that we can measure that location. But that's not quite accurate. So there's two things wrong with that statement. The first wrong statement is that we can't measure the probability of where an electron is around the electron cloud because it's everywhere at the same time. So the electron exists at every location at the same time. But what we can do is we can measure the probability of where it would be at that location on the instant we measure it. The other thing that's incorrect is that there isn't a cloud of where the electron can be, or a probability cloud. There's different shapes based on the energy level, the orbital, and the spin of the electron. So what we're looking at here is the hydrogen wave function, or the probability density of where the electron can be on any given measurement. So when we're looking at these pictures, if we look at the top left one, the electron has the smallest probability, that's where the negative sign represents, or purple, on the outside, or farther away from the nucleus, and a higher probability as it gets closer to the nucleus. But again, the electron is everywhere at once, and we don't know where it is until we measure it, and that's called the collapse of the wave function. As we can see, as the orbital spin and energy state changes of the electron around a hydrogen atom, that not only do we get different locations of where the electron is everywhere at once, but we also get different probabilities of where we would measure it when we measure that electron's states. The first thing that we'll write down is that an electron exists at multiple locations at the same time. An electron exists in multiple locations at the same time. In other words, it's everywhere at once around the nucleus. However, we don't know where it is until we measure it. So we can measure, its probability of locations. We don't know where it is because it's everywhere at once, and we could determine its location once we take the measurements. Now, this idea baffled Einstein that an electron exists in, we could say, multiple states at the same time, or multiple locations, or have multiple intrinsic properties at the same time until we measure it. So Einstein went to his friend Schrodinger and he said, "Hey Schrodinger, are you telling me that if I have some gunpowder in my hand, that the gunpowder is both in a state of nothing, just sitting there, and simultaneously in a state of exploding?" And Schrodinger said, "Yeah, Einstein, that's exactly correct if we're looking at the microscopic scale or quantum scale of an electron." And then Schrodinger said, "That's a really good analogy, Einstein, and even though you're trying to disprove physics, you're actually strengthening it. But I'm going to use a better analogy, and that analogy is Schrodinger's cat." What Schrodinger said is that if we take a cat and put it inside a sealed box with poison in a flask and a radioactive source, that if that radioactive source decays and causes the flask to crack, it'll release the poison and therefore killing the cat. Now, according to quantum physics, the cat is both dead and alive at the same time. So if the box is sealed, we don't know whether the cat is dead or alive. So we have to say that the cat is both dead and alive simultaneously. And that's called superposition. The other thing that disturbed Einstein was the spin state of electrons and how they could be coupled together. So for instance, if one electron has a spin up, then its paired electron has to have a spin down. Einstein thought, well, what would happen if you take an electron, put it inside an envelope, and let's say we go really far away in the universe, and then somebody on Earth has a corresponding electron also in an envelope. According to Schrodinger's cat, those electrons are both spin up and spin down simultaneously, so they're in a state of quantum superposition. But Einstein said, according to quantum physics, that if the person across the universe opens up their envelope and discovers that their electron is spin up, then simultaneously the person on Earth, their electron is automatically spin down. This is called quantum entanglement, where these electrons are interacting with each other faster than the speed of light. And although Einstein said this was impossible, yet again, by trying to disprove quantum physics, he actually strengthened it. Schrodinger went on to win the Nobel Prize for developing the Schrodinger's equation, which describes the quantum state of a particle. And the equation is I h bar d psi dt equals h, the Hamiltonian, times psi of t. Nothing you need to know for Regents physics, but I hope you enjoyed this video and found some of it useful. And thank you for watching. See ya!